Welcome to our journey into the world of materials engineering. This field is all about understanding and manipulating the substances that make up everything around us. From the steel in skyscrapers to the silicon in your smartphone, materials engineers play a crucial role in shaping modern life. In this video, we'll explore the key concepts and real-world applications that define this exciting discipline. Whether you're curious about how bridges stay strong or how new medical devices are created, materials engineering is at the heart of it all. Let's dive in and discover what makes this field so essential. The core of materials engineering are the materials themselves. These include metals, ceramics, polymers, and composites. Each type has unique properties that make it suitable for specific uses. For example, metals are often strong and ductile, making them ideal for construction and transportation. Ceramics can withstand high temperatures, while polymers are lightweight and flexible. Composites combine the best features of different materials. Understanding these building blocks is the first step in mastering materials engineering. Structure of a material, how its atoms and molecules are arranged, directly affects its properties. For instance, the difference between soft graphite and hard diamond comes down to how carbon atoms are bonded. Materials engineers study these structures at various scales, from the atomic level up to the macroscopic. By manipulating structure, they can tailor materials to meet specific needs, such as making glass stronger or metals more resistant to corrosion. Processing refers to the methods used to shape and treat materials. Techniques like casting, forging, extrusion, and 3D printing allow engineers to create components with desired shapes and properties. Heat treatments can make metals harder or more flexible, while chemical processes can add protective coatings. The choice of processing method can greatly influence the final performance of a material, making this a key area of study in materials engineering. Metals are among the most widely used materials in engineering. Their strength, ductility, and conductivity make them essential for everything from bridges to electronics. Common metals include steel, aluminum, and copper, each with its own set of advantages. Materials engineers work to improve metal properties, develop new alloys, and find ways to recycle metals efficiently. The ongoing innovation in metal technology continues to shape our world. Ceramics are known for their hardness and ability to withstand high temperatures. They're used in everything from pottery to advanced aerospace components. Unlike metals, ceramics are brittle, but their resistance to heat and corrosion makes them invaluable in many applications. Materials engineers develop new ceramic materials for use in electronics, medical devices, and even armor. Their unique properties open up a world of possibilities. Polymers or plastics are everywhere in modern life. Their lightweight, flexible nature makes them ideal for packaging, clothing, and countless other products. Materials engineers work to create polymers with specific properties, such as increased strength or biodegradability. Innovations in polymer science have led to everything from medical implants to high-performance sports gear. The versatility of polymers is truly remarkable. Composites combine two or more materials to create something stronger or more versatile than the individual components. Think of fiberglass or carbon fiber. These materials are lightweight yet incredibly strong. Materials engineers design composites for use in aerospace, automotive, and sports industries. By carefully selecting and combining materials, they can achieve the perfect balance of strength, weight, and durability. Using the right material for a specific application is a critical skill for materials engineers. They must consider factors like strength, weight, cost, and environmental impact. For example, the material used in a car's frame must be strong yet lightweight, while medical implants require biocompatibility. The selection process often involves trade-offs and careful analysis to ensure the best performance and safety. Before a material can be used in a product, it must undergo rigorous testing. Materials engineers use a variety of tests to measure properties like strength, hardness, and resistance to wear. Quality control ensures that every batch meets the required standards. This process is vital for safety, especially in industries like aerospace and construction where failure is not an option. Sometimes materials fail unexpectedly. When this happens, materials engineers conduct failure analysis to determine the cause. Was it a flaw in the material, a design issue, or improper use? By understanding why a failure occurred, engineers can prevent similar problems in the future. This process is crucial for improving safety and reliability in everything from airplanes to household appliances. Sustainability is becoming increasingly important in materials engineering. Engineers are developing new materials that are more environmentally friendly, such as biodegradable plastics and recyclable metals. They also work to reduce waste and energy consumption during manufacturing. By focusing on sustainability, materials engineers help create a greener, more responsible future. Nanomaterials are engineered at the scale of atoms and molecules, often less than 100 nanometers in size. These tiny materials can have extraordinary properties like increased strength or unique electrical behavior. Nanomaterials are used in everything from electronics to medicine, opening up new possibilities for innovation. Materials engineers are at the forefront of this cutting-edge field. Materials are specially designed for use in medical applications, such as implants, prosthetics, and tissue engineering. These materials must be compatible with the human body and often need to interact with biological systems. Materials engineers work closely with doctors and biologists to develop safe, effective biomaterials that improve health and quality of life. Smart materials can change their properties in response to external stimuli, such as temperature, pressure, or electric fields. Examples include shape memory alloys and self-healing polymers. These materials are used in everything from aerospace to wearable technology. Materials engineers are constantly finding new ways to harness the potential of smart materials for innovative applications. Electronic materials are essential for the devices we use every day, from smartphones to computers. These include semiconductors, conductors, and insulators. Materials engineers develop new electronic materials to make devices faster, smaller, and more efficient. The rapid pace of innovation in this area is driving the digital revolution. Magnetic materials are used in everything from electric motors to data storage devices. Materials engineers study how to enhance magnetic properties for better performance. Advances in magnetic materials have led to more efficient motors, improved medical imaging, and even new types of memory for computers. Optical materials control the way light passes through or is reflected by a substance. They're used in lenses, lasers, and fiber optics. Materials engineers develop new optical materials for applications in telecommunications, medical devices, and even solar panels. The ability to manipulate light opens up a world of technological possibilities. Understanding how materials respond to heat is crucial in many engineering applications. Some materials conduct heat well while others act as insulators. Materials engineers design products that can withstand extreme temperatures or efficiently transfer heat, such as engine components or thermal insulation for buildings. Mechanical properties like strength, toughness, and elasticity determine how a material behaves under force. Materials engineers test and modify these properties to ensure materials can handle the stresses of real-world use. This is especially important in construction, transportation, and manufacturing industries. Corrosion is the gradual destruction of materials by chemical reactions, often with the environment. Materials engineers develop coatings and treatments to protect metals and other materials from corrosion. This work is vital for infrastructure, transportation, and any application where durability is key. Materials engineering plays a huge role in construction. Engineers select materials that provide strength, durability, and safety for buildings, bridges, and roads. Innovations like high-performance concrete and advanced steel alloys have revolutionized the construction industry, making structures safer and longer-lasting. From cars and airplanes to trains and ships, transportation relies on advanced materials. Lightweight composites and high-strength metals help improve fuel efficiency and safety. Materials engineers are constantly developing new materials to meet the demands of modern transportation, making travel faster, safer, and more sustainable. Electronics industry depends on materials with precise electrical properties. Semiconductors, insulators, and conductive metals are all carefully engineered for use in devices like smartphones, computers, and televisions. Materials engineers push the boundaries of what's possible, enabling smaller, faster, and more powerful electronics. Medical devices, implants, and diagnostic tools all rely on specialized materials. Biocompatibility, sterilizability, and durability are key considerations. Materials engineers collaborate with healthcare professionals to develop safe, effective solutions that improve patient outcomes and advance medical technology. Energy production and storage depend on advanced materials. Solar panels, batteries, and wind turbines all require materials with specific properties. Materials engineers develop new materials to improve efficiency, reduce costs, and support the transition to renewable energy sources. Aerospace engineering demands materials that are lightweight, strong, and resistant to extreme conditions. Composites, titanium alloys, and advanced ceramics are commonly used in aircraft and spacecraft. Materials engineers help push the boundaries of flight and space exploration by developing materials that can withstand the harshest environments. Sports equipment has been transformed by materials engineering. Lightweight composites, advanced polymers, and high-strength metals are used in everything from bicycles to tennis rackets. These innovations help athletes perform better and stay safer, showing how materials engineering impacts even our leisure activities. From the clothes we wear to the packaging that protects our food, materials engineering touches every aspect of daily life. Engineers work to make materials safer, more durable, and more sustainable, improving the quality of life for people around the world. Research is the driving force behind advances in materials engineering. Scientists and engineers collaborate to discover new materials, improve existing ones, and develop innovative processing techniques. This ongoing research leads to breakthroughs that shape industries and improve our lives. Materials engineering is a highly interdisciplinary field. Engineers work with chemists, physicists, biologists, and computer scientists to solve complex problems. This collaboration leads to innovative solutions and new applications for materials in a wide range of industries. Modern materials engineering relies heavily on computer simulation and modeling. These tools allow engineers to predict how materials will behave under different conditions, saving time and resources. Simulation helps optimize designs and accelerate the development of new materials. Additive manufacturing, or 3D printing, is revolutionizing the way materials are processed and used. This technology allows for the creation of complex shapes and customized components with less waste. Materials engineers are developing new printable materials and exploring the possibilities of this exciting technology. Recycling is a key part of sustainable materials engineering. Engineers develop processes to recover and reuse materials from old products, reducing waste and conserving resources. Advances in recycling technology are making it easier to close the loop and create a more circular economy. Despite incredible progress, materials engineering faces many challenges. These include developing materials that are both high-performing and sustainable, reducing costs, and ensuring safety. Engineers must also keep up with rapidly changing technology and evolving industry needs. The future of materials engineering is bright, with trends like smart materials, nanotechnology, and green manufacturing leading the way. Engineers are exploring new frontiers, from self-healing materials to biodegradable plastics. These advances promise to make our world safer, cleaner, and more efficient. Career in materials engineering offers endless opportunities. Students learn about chemistry, physics, and engineering principles, preparing them for roles in research, manufacturing, and product design. The demand for skilled materials engineers is growing as industries seek innovative solutions. Women are making significant contributions to materials engineering, breaking barriers and leading research in many areas. Encouraging diversity in the field brings fresh perspectives and drives innovation. The future of materials engineering is stronger with more voices at the table. Ethical considerations are essential in materials engineering. Engineers must ensure that materials are safe, sustainable, and used responsibly. This includes considering the environmental impact, health and safety, and the long-term effects of new materials on society. Materials engineering has a profound impact on the global stage. From supporting infrastructure in developing countries to advancing technology worldwide, materials engineers help solve some of the world's biggest challenges. Their work improves lives and drives progress across the globe. Let's look at a real-world example: skyscrapers. These towering structures rely on high-strength steel, reinforced concrete, and advanced glass. Materials engineers select and test materials to ensure safety, durability, and energy efficiency. Their expertise makes modern city skylines possible. Smartphones are a marvel of materials engineering. From the tough glass screens to the tiny semiconductors inside, every component is carefully designed. Materials engineers work to make phones lighter, stronger, and more energy efficient, enabling the technology we rely on every day. Medical implants such as artificial joints and heart valves depend on advanced biomaterials. These materials must be strong, durable, and compatible with the human body. Materials engineers work to develop new implants that improve patient outcomes and quality of life. Renewable energy technologies like solar panels and wind turbines rely on specialized materials. Materials engineers develop new materials that improve efficiency, durability, and cost-effectiveness, helping to make clean energy more accessible and reliable. Materials engineering is a dynamic and vital field that shapes the world we live in. From the tiniest nanomaterials to massive infrastructure projects, materials engineers are at the forefront of innovation. As technology advances and new challenges arise, their expertise will continue to be essential in building a better, safer, and more sustainable future for everyone.